The final topic I'd like to talk about with electronic spectroscopy is, since we have delta V can be anything, there are still some limits on what we'll actually observe when we do the spectroscopy. So which transitions will we see? So in the previous example I showed with calcium oxide, there were specific quantum numbers, differences in quantum numbers that we saw. We saw 0 to 8, 0 to 9, but we didn't see 2 to 5 or 2 to 10. And there, why is that? And then the other question is, how strong will those transitions be? Why were some transitions taller than other ones, even in the spectrum that I saw? There are two main factors going on here. The first has to do with what we call population. Basically, are there molecules that are in that particular state? Is there anything to transition from the lower state? Right? So are molecules in a particular V value? And this is largely depends on temperature. Right, so at low temperatures or normal room temperatures, room. At room temperatures, mostly everything will be in the V equals 0 state. Maybe a little bit in V equals 1, but for almost all molecules, everything will be essentially in the V equals 0 state. So you'll only see things that have a lower value of V equal to 0. And this will relate to absorption spectroscopy. For emission spectroscopy, it depends how you are exciting your molecules to then see their emission of light. So is there, are you exciting it by heating it up, or are you exciting it using a laser or using electricity, right? Depends. That'll determine whether you get population of molecules in a particular V value. So it depends on how you're exciting. Okay, so then the second key point as to how strong transitions will be and whether you'll see them or not is how well do their wave functions overlap. And this idea is known as the Franck-Condon principle. And so the idea here is that for a transition to occur, there has to be a significant overlap of the vibrational wave functions. And the reason for that is the strength of our transition depends on an integral. We'll get to these figures down here in just a second. But the strength is proportional to an integral that depends on the wave function, the overlap of the wave function in the upper state and the wave function in the lower state. Right, and so if these wave functions are very far apart from each other in space, spatially speaking, the overlap will be poor and you won't get a very strong transition strength. On the other hand, if they overlap really well, you get a very strong transition. And what's going to affect this is how well the overlap is as you move from one state to another. And so these are a couple of figures from your textbook illustrating this principle. So in the first one, we'll look at the first one. Let's do green. So in the first one, we have something with a similar bond length in the ground and excited state. So we have, basically where this bottom of this potential is about the same R distance. And what matters here is what's the overlap between, we're going to assume our molecule starts just in the V equals 0 state, and this wave function here represents the wave function, the vibrational wave function for a V equals 0 state. And we want to know the Franck-Condon principle states that the molecule will basically move, before the bond length can adjust, the molecule will move directly vertically along this potential energy curve when it's excited by a photon. And so we see between the V equals 0 and V equals 0 levels here, their maxima are at about the same bond length, and we get good overlap. And so in this case where the bond length is similar, this would be a very strong transition. And then as we go to the first excited state, we'll use a different color here, as we go to this one, we see now where the v equals 0 state has a very strong, very high probability in the middle, that's where you have a node in the v equals 1 wave function. So if we were sort of to plot this out, if we plotted out the absorption of light versus frequency along this axis here, for v equals 0 to v equals 0, we'd see a strong transition, then a weaker one for 0 to 1. And if I've kind of need to erase a little bit here, but if you look at the next one up, v equals 2, we see again that there's not a node there, there's a little bit more, and so that'll be strong, a little bit strong again, and then it'll get weak again. And so 0 to 1, 0 to 2, we see this pattern that develops, and this is due to the Franck-Condon principle. Now, on the right-hand side, the bond length is a little bit longer in the excited state. And so this whole thing has shifted just a little bit to the right. It's a little bit subtle to see. But the key point that we'll see here is now where there's a maximum here in the ground state, if we go directly up, it no longer coincides with the maximum in the v equals 0 level for the excited state. And so now we'll see something for this spectrum, if we plot it out, where the 0 to 0 transition is now weak. But there is good overlap as we look at this, right, if with the v equals 1 state, and so it'll increase. And so this overlap is really what matters, and we get a very different pattern depending on how these wave functions overlap between the ground and excited state. And so we can take advantage of this fact and make predictions. If we can calculate bond lengths in the excited state, we can make predictions about what we would expect to get for the strengths of our electronic transitions and see if that matches what we actually observe. So this is yet another thing we can take advantage of when we're doing experiments and comparing it to theoretical calculations.